Hello everyone, in this video we're going to discuss the kinetic energy associated with rolling and how we can combine the rotational and translational kinetic energy, and then we're going to use that and apply it to an interesting example involving rolling objects. Okay, so right here we have that when we're talking about kinetic energy, we talked about how an object, let's say that's moving in a direction, has some translational kinetic energy, and an object that is rotating also has some kinetic energy, and we called it k rot for rotating. But if an object is doing both, then it's going to have both energies. And so as just a reminder, the rotational kinetic energy is this rotational inertia times the angular velocity squared, and the kinetic energy of translational motion is 1/2 mass times the velocity translational squared. Okay, and so when we have rolling, when we say something is rolling, we're usually going to have a situation where there's no sliding. Sometimes it could be called like perfect rolling, and this is where, let's say you have like a ball that's rolling, it's going in this direction and there's no slipping with the ground. And that means that there's no friction that's dissipating the energy. So when there's no sliding, we're going to have no dissipation of the kinetic energy for the rotational or the translational. Okay, so there'll be no dissipation due to friction. And so, yeah, but if there is sliding, then there is going to be some dissipation of this kinetic energy, and so you won't be able to relate it as conservation of energy. And so let's say we have a situation where there is no sliding, which means there's no slipping, there's no conservation of energy. We had these equations from before where like the x distance equals the r times theta, the velocity equaled the r times the angular velocity, and the acceleration equaled r times the angular acceleration. Well, when there's no sliding, we can actually just say that this is the x of the center of mass of a rolling object, and this is the velocity of the center of mass and the acceleration. And that's because at each point, we can think of it's like sticking to the ground. So if each point is rotating around with some velocity, so is the center of mass since there's no sliding. And you can kind of think of it like a gear with the ground. It can only rotate as fast as it can move across the ground if there's no sliding. But if it can spin around a bunch and not move as far, then the center of mass is not going to relate directly to these relationships that we talked about earlier. It's only if there's perfect rotation and perfect rolling without any sliding. Okay, so let's apply this to an example where we have rotation. Okay, so we have a thin hoop with a rotational inertia of mr squared and a solid cylindrical disk of 1/2 mr squared are released from rest at the top of a ramp. The objects roll without slipping down a ramp. Express each object's final velocity in terms of the height of the ramp to determine which one reaches the bottom first. Okay, so let's draw out this situation here. So we have a ramp, okay, and so we have a case where we have a solid disk that's rotating and rolling down, and then in the other situation, we have a thin hoop, which we can think of like this. Okay, and so this is also going to rotate and roll down the ramp. So now let's compare the top and bottom spots. So when it's at the top, we can call this height h naught for both of these. The velocity, v naught, is just going to equal 0 because it's released from rest in both of these cases as well. And same with the angular velocity since it's released from rest. And now when it reaches the bottom, we're going to have a height equal to 0. So we'll call our reference height like the bottom of the ramp. So that's h equals 0 at the bottom. Okay, so that's when we can say there's no potential energy because that's where we're defining our reference from. We have to define a reference somewhere. Okay, we'll also have a velocity final and an angular velocity final. So we're asked to relate the final velocities, so we'll talk about the translational velocity or the velocity of the center of mass that each one of these has. Okay, so now we can just compare them. So let's start with the cylindrical disk. So we know that we're going to have some kinetic energy initial, and this will be the disk. Okay, so we're going to have kinetic energy initial plus the potential energy initial, and this is for gravity, equals the kinetic energy final plus the gravitational final, right? And so as we talked about before, since this is rolling down the ramp, it's going to have both of these. But first of all, since it's at rest, there's going to be no initial kinetic energy for rotation or translation. And when it reaches the bottom, we define that as h equals 0, so there's going to be no potential energy final. And so we're only going to have this initial and final for the potential and kinetic. Okay, and so we can rewrite these now as we'll say RU sub gravity, and the kinetic energy final, which as we talked about is the final rotational energy plus this kinetic translational energy. Okay, and so we know gravitational potential energy is just mass times gravity times height, and so this height is going to be h naught, which we'll just call h in this case. And the rotation is going to be the 1/2, and this I is going to be of the disk, so we'll say I of d. And then we have the rotational, or the angular velocity squared, plus 1/2 the mass times velocity squared. Okay, and so we're supposed to just relate this final velocity in terms of just the height of the ramp and any constants. And so to do this, something is going to need to start canceling out. So let's rewrite this. This part we already have as its final variables, but we were told what the rotational inertia of the disk was, and we see that it's 1/2 mr squared. So we can actually plug in 1/2 mr squared here, and then we still have this angular velocity squared plus 1/2 mvf squared. Okay, and so you'll notice here the masses in this case cancel, but we still have to do something about these angular velocities and the radiuses. And so we know, since we have this rolling relationship, we learn that the velocity of the center of mass, or the translational velocity, since it's sliding, it's going to be not sliding, it's rolling, it's going to be the same thing, is just radius times this angular velocity. And so we can rewrite this as angular velocity equals the velocity over the radius. And so now we can start plugging those in. So we have gh equals, I'll combine these fractions to be 1/4 radius squared, and this is velocity over radius, and this whole thing is squared, plus 1/2 vf squared. And so this will be the final, because we're looking at the final rotational velocity as well. And so now this radius is going to cancel with this one, because this is going to be squared, but this whole thing is squared. And so we just get gh equals 1/4 vf squared plus 1/2 vf squared. And so we can go ahead and combine some terms here, and I'll just multiply by 4 to make this a little bit easier. And so if we rewrite this, if we combine our velocities and divide, we get that the velocity final squared equals 4/3 gh, and so this velocity final is going to be the square root of 4/3 gh. And so we got this without having it depend on the mass or the radius, which is important. And so this is for the cylindrical disk. Okay? And so now let's do this same process just for the hoop. So now we'll do it for the hoop. And so I'll save some time here. We know that just because it changes, we're going to get to the same point for the hoop, just with variables for the hoop, because it's still not going to have any initial kinetic or final potential, and we're just breaking these up. So I'll go ahead and start at this point, because that's where things are going to get a little bit different. So we're going to have the mass times gravity times height equals 1/2 this rotational inertia of the hoop, angular final squared plus 1/2 mass velocity final squared. Okay, and so the main difference, really the only difference we're looking at here, is this rotational inertia. And so for the hoop, we were told, and we should really know this, is that the rotational inertia is just mass times radius squared, because it's treated as a thin hoop, right? So we just have mr squared. And we can do the same thing with this final angular velocity and just say it's the velocity over the radius squared, because it's also rotating without sliding, plus 1/2 mvf squared. And so now we'll get a bunch of things to cancel out. So the masses cancel again. These radiuses are going to cancel. And we will end up with just GH equals 1/2 V squared plus 1/2 V squared. And so this is just going to be V squared equals GH, because these two just equal 1 V squared, and then we can get our square root, and this is our final answer. And so now we can see that this is for the hoop. The hoop is going to have less velocity when it reaches the bottom, which means it's going to reach the bottom slower because it has less velocity. So the velocity final of the disk, we'll say cylindrical disk, is greater than the velocity of the hoop, which means this one's going to reach the bottom faster. And so the important relationship here is that this final velocity and the speed it gets down the ramp does not depend on radius or the mass of the object. It only depends on this rotational inertia, and which really, when we think about it, makes sense, because if we're trying to have something rotate when all the mass is closer to the center, that'll be easier to do rather than all the mass being far from the center. And so that's why this one takes more energy to rotate down this ramp than the one where the mass is more evenly distributed and the more mass is near the center of mass. And so that is why it'll reach the bottom faster if it's a solid sphere or if more of the mass is in the center, rather than if it's more mass far away from the object, proportional to its mass, since the total mass doesn't actually affect the speed. So that was kind of just an interesting relationship that you can derive using these rotational and translational kinetic energies. So I hope that was interesting. Leave your questions in the comments, and thanks for watching.